Hi, everybody. I'd love to introduce Julie Heinrichs from Conventional Ecology Group and Colorado State. And yes, she has done a ton of fantastic work on modeling forests and their ecological dynamics. Welcome, Julie.
Thank you. Thanks for the invite to talk about a topic that I have spent a lot of time thinking about and love to talk about, which is using ecological simulation models to forecast species and landscape change. So I got into this line of work because I was thinking a lot about ecological complexity. As we look across our environments, we see that the environments have radically different conditions from place to place and from time to time. And this can incite a lot of differences that matter for animal responses and plant responses. And one of the challenging aspects of working in complex systems in this contemporary day and age is that a lot of the tools that we've traditionally relied upon don't work as well as we're departing from historical conditions, and the patterns and processes that were operating in the past are starting to kind of dissolve and disassociate and change into new things. So here's an example of the Mazama pocket gopher in Washington, where change is quite dynamic. As a result of extreme weather, we're simulating them to have pretty dynamic occupancy and densities. There's hot spots and cold spots of change. The pace can be incremental or it can be sudden. In this case, we're trending in a kind of downturn direction, but there are moments in time where the change is positive for the species. So this kind of dynamism is a particular challenge in ecological research. Another challenge is this idea of cascading changes, and climate change is a good example of this. We think classically of climate changes in temperature and precipitation, and those kind of envelopes of climate space moving through time. But there are cascading influences of those things on a number of system components. Temperature and precipitation affects vegetation, and they can transition to other states. There can be succession, or there can be invasion, and a number of other things. And for wildlife, they perceive these differences as changes in habitat. They start to use the landscape in different ways and move in different ways. Climate also affects how we develop and use the landscape, which animals also respond to. Climate can cascade through that system and affect populations, but it can also kind of like skip and directly influence individuals in inciting some like physiological stress or like heat stress. There's changes in competitors and communities. So there's lots of different ways that many of these problems show up in environmental systems. So this is one example of kind of like a wicked environmental ecological problem. So we term these as things that are kind of have multiple interacting factors and pathways of influence or impact. They tend to be pretty large scale and long term. They have some uncertainties and unknowns that can lead to some decision paralysis, debate on how to deal with the situation and how to prioritize different kinds of needs. So this is kind of like the motivation for me to kind of dig into ecological simulation modeling and to seek a solution or a platform to really start modeling how to understand these complex ecological systems. What are the key mechanisms, the components, the uncertainties, and what can we use these tools for in terms of simulating adaptation or ways to just try to start tackling these wicked problems. So I'm going to talk today mostly about individual-based models that are mechanistic, but lean on aspects of statistical and spatial projections. And you can think of them in essence as this kind of structure where you have these interacting components. So as the environment changes, we have things like behavior change and demography change. So for example, as climate changes, we have fire frequencies and regimes change, more habitat is burned. We may install fuel breaks that cars also use, so animals may not then be willing to traverse the landscape the same way they used to. As their movement behavior changes, they'll have demographic consequences. So they could stay in areas that have low mortality in their safe zone, and perhaps not cross into an area that has higher mortality with predators and community changes. But when you scale it from the level of the individual to the population, we can look at how the kind of system and the changes to the system may influence populations into the future in terms of their abundance and their distribution. So by individual models, I mean, we're talking about simulations that focus on individual agents. So in wildlife ecology, we think of those as individual animals or plants, but they essentially just differ from each other based on their history or their traits. They can make decisions independently with whatever criteria you supply to them. A key concept is the idea of emergence, where although you're tracking individuals and kind of programming them to move and behave and respond in certain ways, when you scale up to the higher level order, for example, at the level of the population, you see patterns and processes emerge that can be unexpected. So the kind of modeling I'm talking about today is also spatially explicit. So we're representing locations of individuals and objects and space in general, and the complex dynamics that individuals have with that environment. So we're looking at a static map here, but we can also have dynamic maps and maps created on the fly as individuals change their environment or as scenarios change the environment.
So question, how do you provide the input data for a model like this? I mean, landscape, I guess maybe satellites, but individuals, that's extremely challenging, it seems.
Yeah. So it varies from case to case. Some species will have a host of information, locations, will have summaries of how they move. We'll sometimes have GPS track logs of where they've moved to, and we can create summaries of that and representations of that information. For other species, we are dealing with a little less information in terms of how they would move, but I'll show you in a few examples here some of the ways that we put info into these models.
Thank you.
So the models that I'll show you today are built in the HexSim modeling platform. They're a framework for creating these spatially explicit individual-based population simulations. This is work by Nathan Shoemaker et al. At US EPA. And if you're interested in learning a little bit more about this, you can find it on the website. There's some resources there and a free download. So this is open to anyone to kind of use and play with. But whether using that framework or others, the workflow for kind of creating these IBMs is roughly as follows. I often work with people that have very specific project objectives in terms of conservation or a scientific question. So we collaborate and co-design the project and its objectives and what the model needs to accomplish to be actionable. We are working with experts to look for data sets, and we comb the literature, we create extensive spreadsheets of what's known about a species from external resources. We do interviews, we do stats and all sorts of background analysis on the data sets that we find. And we spend a good time planning the model and its integrations. We ultimately build and test it, and then verify the output that comes out of the model with some sort of real pattern and process data. So that could be where animals have been found in the past, or how they've moved through the landscape, or what habitat they've chosen to live in. Once we're happy with how that looks and it's approximating reality in a good way, we build these scenarios to look at variations to explore different questions, and then run those forward in time and collect our results.
So question, how long does one of these cycles take? Like how many times or many scenarios can you replicate this for?
I mean, the only limit to the number of scenarios is the number of computers and the amount of time you have available for a project. Some simulations will run really quickly, like in minutes, and others, depending on how big and how many individuals you have in the landscape, how many tough processes you have in the, like, chunking through the code, it could take days or weeks. So it's
Okay.
totally
And
different.
then like data collection, like the entire process, because it seems like
Yeah.
most time will be the human time. Is that fair?
Yeah, most of it's human time. And if it's a simple model with a simple question, one could do it in a week. If it is a pretty exhaustive review of information and consultation and elicitation and all sorts of background analyses that have to happen, it could be years.
Makes sense. All right, thank you.
So the data that we put in these things vary pretty greatly. And I think that's one of the great strengths of this kind of approach, is that we can have, data in spreadsheets or maps or point estimates or statistical distributions, thresholds or relationships, and we can get those for anything that relates to spatial, population, or mechanisms that relate spatial and population together, factors that describe change, or things that we would do to the ecological system to modify it. So I guess at its core, we try to add this information in various ways. And we program individuals with their traits, and we can transition them among different categories with different rules. So things like ages or behavioral states or resource needs or perceptions. We can use maps as both like input information and output information, and a way to kind of translate information from one individual to another within the simulation. We can work with numbers in ways that are pretty flexible too. So random number generators and equations and math and so forth. Because at their core, IBMs are usually stochastic, so that there's a bit of randomness to each element, and then you conduct a number of repetitions and then look at all the results together to kind of bound the possibilities. But most of them are user defined, so they're quite flexible in using all that range of information. And they're scalable. So if you're using a flexible platform or creating your own, you can make a model that is incredibly simple and incredibly fast, and really parsimonious. And you can also make something that is highly realistic and detailed and complex, that is a very convincing analog of a real system. But one of the strengths is this scenario-based experimentation. So when we're thinking about uncertainty and potential future alternatives, exploring a number of different options is a really interesting line of work.
So question on this, how do you know when to stop adding detail? Because one neat thing about ABMs is you can get a lot of realistic emergent behavior from simple rules, except it's hard to know when you've gotten all the dynamics in reality, given how little information you have about reality realistically.
Yeah. So one of our benchmarks is defensibility. So when we build models, we think about what information can we point to that demonstrates that that is actually what's happening in reality and is important for the system and the question. So if we can't point to a data source or a citation, then the inclination would be to leave it out of the model unless we think it is an essential component that is just an unknown, in which case we may choose to represent it, but simply. I think there's always a desire to add more information, but if it doesn't serve the particular question, it can weaken the model ultimately by adding complexity that is either difficult to defend or just increasing the intractability of the model that you create. So we're quite mindful of how to construct realism without weakening the system, if that makes sense.
That makes sense. Yeah, thank you.
So I've got 3 examples to show you today. They're all kind of wildlife IBM applications. Some of them are looking more to characterize the ecological system and trajectories and think about uncertainties. Some are looking more at the drivers of change and the thresholds of change. And others are geared more to thinking about developing long-term and future plans. But these will vary a little bit in their complexity and realism too. So maybe you'll get a sense of how they can vary and why we've chosen to go more complex in some situations than others. So the first example is work that I co-developed with the U.S. Forest Service, looking to model historical occupancy of the red tree vole in Oregon and California. And the motivation behind this project is the idea of forest change. In particular, old growths are declining globally, and this is happening particularly fast in Oregon and California with land use change and timber harvest. And you probably all recall kind of some pretty epic wildfire seasons in the recent past. And these combination of factors can be pretty challenging for the species that depend on these older trees. So the red tree vole is a species of concern. They live high up in the trees. They only move very short distances, and they try to do so from tree to tree and not on the ground. They're elusive. They're hard to find. In fact, we have to climb trees and find voles in nests to kind of confirm their occupancy. That's hard-won data that does not exist across the species range, but in pockets where we've been able to sample particular locations. But we know that the landscape is changing everywhere. So the question for this species is, what is the likelihood of changes to the forest really impacting changes to the population? How do we extrapolate the information that we have across that geography? So we're asking questions like, how many tree voles could there be across this large area? And where are they most likely to be found given how habitat has been and how it's changed? So we look to these dynamic spatial IBMs to model this, in part because they're really good at kind of linking habitat change to population change. There's enough functionality there to make that linkage clear. And to do so in a biologically nuanced way, so that our estimates of how many voles there could be include how far individuals can move, their population dynamics across vole generations, and the timing of all the changes. And ultimately wanted to use the results to think about land management plans into the future. So we started with developing a habitat change model. So Mark Linnell here used a bunch of remote sensing inputs that characterize forest structure and composition, some climate variables, paired that with those nest locations high up in the trees, uses statistical modeling approach, and then Google Earth Engine to extrapolate across space and time, those relationships. And then we had this time series of mapped habitat. So this is kind of a data light extrapolation to get a pretty rich time series of maps that we could investigate forest change. We paired that information with life history, population, and some ways in which we know the animal uses habitat and space, and put that in our individual based model. So we essentially populated the model with tree voles at an abundance and in density, putting them in locations that we thought were higher suitability locations from our habitat map. We allowed the individuals to kind of go through this cycle of events, starting with survival and aging, and then kind of 3 pulses of breeding and reproduction in a year. And then we would swap out the old habitat map for a new habitat map, and then time would increment. We would repeat this process through the 36 years and several replicates, and then combine all the results to look at what the potential impact to populations would be under different scenarios. So kind of our key findings included that we saw a fair bit of loss of habitat, and here you're looking at purple occupancy of tree boles changing through time, and accelerating change in occupancy and abundance towards the more recent years. And the rates really kind of vary across space, but the eastern area there, the Cascades, had a fair amount of change in recent years in particular. The blue is suitable habitat, but it's not particularly occupied. So you see this diminishing occupancy and abundance.
Wait,
And
Roland,
go ahead.
Yeah, I'm curious how the simulated results are validated in terms of kind of confirming whether or not that I get that, especially with occupancy modeling, it's a latent variable, so there's really not good ground truth, but how y'all are validating whether or not that is true. I know that you kind of mentioned some other data and citations, but could you talk a little bit more about how the results, given that simulation based, is confirmed to be an actual phenomenon?
Yeah, so there's two things that we think about. One is in kind of like the model verification process. So when we're building the model and seeing some of the initial results, we're comparing patterns that we see coming out of the simulation model to empirical data. So we don't know where occupancy is everywhere for the tree wall, but we can look at where we have known occupancies at certain points in time. So as we run the model, and here we're starting like back in 1986, as we run it into time steps where we have those slices of information, we can look to see, yes, there was occupancy in the place that we predicted it to be in the simulation. Where we don't have information, we can't make the same comparison, but we can look at the patterns and the processes and kind of get a sense of, is it operating realistically? And there are other ways, like if we were to withhold some of the information, kind of like in a testing training situation, that can sometimes be helpful. But overall, when you're making kind of these emergent predictions, you're not necessarily looking for cross-reference to another data set that made this, a similar prediction. Sometimes that's possible, but they're usually different approaches and will tell you slightly different things. Does that answer your question?
Yes, I mean, I have a couple of follow-ups. Do y'all ever leave out the most recent few years and see if it's recovered, kind of as a holdout set of, okay, if you're looking at the forward projections, would it recover, the last few years for which you have data, if you excluded those? Is that something y'all have tried?
Yeah, sometimes that can be useful. And people do that. We didn't do it in this scenario because we had a lack of information in the recent years, and it was a bit spotty, but yeah, that can be a strategy.
And then on the comparing to the empirical data for which y'all do have kind of known occupancy, do y'all use anything like posterior predictive checks for the occupancy models, or is it really just kind of looking at those particular points as kind of the more of a qualitative check rather than quantitative checks?
So we'll do both. Like we'll look, does it generally look right? But we can also look at maps and create difference maps. Was there occupancy there before? Is there occupancy there now? We can also do meta models, like look at where we've predicted occupancy in the simulation model, and then create other kinds of statistical models that look at the variables associated with that and look for correspondence with previous data or previous models and their covariates.
Awesome, thank you.
All right, so another observation is that we saw this intensification of like private public ownership checkerboard. So these adjacent land ownerships had different harvest harvest characteristics, and so through time we saw the loss of a lot of forest, particularly on private and less so on protected lands. So I guess some of the implications of this work was that we were seeing that disturbance is outpacing regeneration, that was leaving us with some clusters of occupancy in these higher density areas of protected forest, but leading to kind of the realization that the tree voles are becoming increasingly fragmented in these disconnected populations. Looking at kind of all tree voles together and an abundance kind of summary here, we saw that, you know, in much of the early time series, the forest change didn't seem to be impacting the population in terms of its potential, the landscape's potential to host that many voles. But then at some point we saw a bit of a decline, and it's unclear whether this is, you know, a decline that the species will recover from, or whether it will the trajectory will continue to decline. That's phase 2, which we haven't completed yet, but it kind of looks here that there could be a bit of a tipping point. And that may be something that we can start thinking about now for monitoring populations in strategic places to kind of identify where and when we might expect some more rapid decline in population abundance. We looked at some alternatives to gauge what unknowns were most important in the model, and the key one that we found was that if we modified this relationship between quality and density of habitat, we had an increased population size and a pretty different distribution. Conversely, if we looked at some other factors, they were less influential, and even like the starting abundance that we would put into the landscape, since that was a bit uncertain, that didn't have much of an influence at all on population outcomes. So that's one way to kind of think about how to manage uncertainty in a species in a landscape for which you have a little less information. So some of the recommendations were to think about monitoring for population decline in specific scenarios where populations are becoming disconnected from each other, and to think about forward-looking plans that allow for voles to kind of grow and persist in place where they can't move elsewhere. Okay, so a slight shift in geography, but not much. Here's a quick example of simulating connectivity for the Humboldt marten. And this species was listed as threatened in 2020, and one of its problems is that it occurs in these like little population areas a little bit around the coast there and in the interior, and we don't really well understand how connected those populations are. Connected populations are important for maintaining genetic diversity, and if that declines, you can have populations that just have poor health and start to decline for those reasons. So this species is pretty mobile. It'll move pretty good distances, and it can cross a number of features, but not all of them. And this is a pretty complex landscape with a lot of rivers and roadways of various sizes and challenges. And there's more habitat out there in this landscape that we think that the marten may not be occupying, but potentially could. And we're wondering if it is an access issue. So one of the questions we were looking at is, to what extent do landscape barriers prevent movement among populations and to unused habitat? What are the features in particular that are kind of interrupting? And if we were to intervene on roads and help by providing some sort of support and having them navigate roads, where should we do that? We created this model, which I won't go in, but we'll talk a little bit about dispersal here. So the way the movement module works for this this species is that individuals are looking to draw a movement distance from a distribution that's characterized from empirical data. They're evaluating their neighboring pixels, and then selecting a higher value pixel is kind of their next step. But they weigh that next step with a number of other decision criteria, including the desire to kind of move more in a straight line than randomly, to avoid certain features like non-habitat or ocean. And they're able to stop early if they find a really great territory. And that's the purpose of them moving, is to find a new territory. Along the way, they're interacting with these barriers, some of which pose bigger challenges than others. Some of them are reflecting features like fenced highways or wide rivers. Others they can go through but have some risk of doing so in terms of mortality, and the small ones are absolutely no problem. So we simulated martins moving out from those population centers into the landscape, migrating through that complex landscape. We had about 700 of them moving in this simulation and tracked them over 100 years, and then looked at where they were able to get to and what restrictions were present to their movements. So if we look here, the green are the road networks, and we saw in blue here kind of high densities of movement. So movement isn't a problem in those blue areas. And then in some areas we saw the green roads really providing kind of a restriction to permeability and moving out into the rest of the landscape, where you see kind of low and black as the areas where they're just not getting to. So some of these roads are also responsible for some simulated mortalities. So some of the recommendations from this work were to think about setting up some targeted monitoring and sampling of martins and moving across select roads, and looking for differences in genetic diversity in some of these populations. Got one more example, and a little bit of time to do it, I guess. So the last one is looking at forecasting the influences of multiple stressors, and our example species here is the sage-grouse. So moving inland here, we're looking at kind of Western United States, and across the range, the species is generally declining. In some places more than others, but in this Wyoming area, that's kind of the stronghold for this species, where they're doing the best. They're using large areas of the landscape, and every season of the year, like spring, summer, winter, they have different habitat needs that we need to represent, and they seek different features. So vegetation is expected to change with climate, and this landscape is also changing with oil and gas development. So one of the questions we were interested in is, what is the potential range of abilities of this species to withstand change in its stronghold? To what extent could incremental changes cause population decline, and where might we see the greatest change in 50 years? And if we think of a couple of these things together, does that change our understanding of risk versus if we just look at one of these independently? So our approach was first to develop landscape projections. So a colleague, Steve Garman, actually created his own IBM that placed oil and gas infrastructure on the landscape and future projection. We also built some climate vegetation projection maps. And with those inputs, we updated spatial statistical models of habitat and created a time series, and then put those into the wildlife IBM to simulate responses to landscape change. So this is a bit more of a data-intensive example. So the development maps included things like past and current active infrastructure, looking forward 50 years. And this model had a number of really kind of interesting practical constraints and designs to it. So it's based on energy field management areas and in polygons where they're planning to build out infrastructure. and a lot of rules about where it would be and the spacing and the expected intensity of development. It also included kind of areas that were set aside for sage-grouse conservation, where there's a bit more protection for them in those areas. So representing some kind of competing land use priorities. We also developed a couple economic development intensity scenarios with essentially different levels of build out onto the landscape. And then where that IBM had placed infrastructure, we removed the vegetation underneath that and then updated the habitat models with that information, also separately with just climate altered vegetation. And essentially got a new set of habitat maps, 3 per year, that we would swap out in the individual base model to represent oil and gas and precipitation-driven climate change every season of every year for 50 years. So here's kind of our nutshell schematic of this IBM, where we're swapping out maps pretty continuously. And as individuals move through the landscape, we're recording their habitat use. This has a lot more wildlife biology programmed into the different areas, with individuals remembering their locations and we're returning to them in subsequent years. And they also had spatially dependent responses for movement. So if they're close to some active wells or haul roads, certain number of them would move away from that location and search for a better spot. They would have reproduction and survival consequences of remaining in that area. And these were all rules that we based on a host of empirical studies done in this region. What we found is that there was a decline in a lot of places in terms of the number of sage-grouse that were persistent on the landscape 50 years into the future. The greatest declines were in these energy project areas that were meant for energy development and less so birds. And conversely, we saw that this kind of compartmentalization of space was useful for sage-grouse in these core areas, at least, helping them to stay afloat in positive numbers in some cases, even though the decline was evident in most scenarios. We also mapped this spatially to kind of look at how this could play out if some of the intervening areas were developed, and found that in some scenarios, there was some risk of disconnecting populations in these kind of core hatched areas from others. The results really varied based on whether the assumptions that we made about the intensity of development as well as how many birds were out there. So that's why we do these different scenarios, to kind of put some bookends on what we know and what we'd like to know in the future about the situation. Some of the takeaways were that if we looked at the changes on an annual basis, they were pretty small. So less than 1% decline per year caused by an individual factor. But through time, that over the 50 years, that caused, a 33 or a 52% decline, depending on if you were looking at one factor or multiple factors combined. And notably, we only looked at two of the important ones, and there are other factors at play in this landscape. So that suggests that our confidence maybe shouldn't be super high that the stronghold of this species is secure into the future. These examples highlighted a lot of things that are kind of going wrong in ecological systems, but this platform is equally good at thinking about and simulating the cumulative benefits of things that we do to intervene, securing land, restoring habitat, lots of specific on-the-ground and place-based population recovery actions, climate adaptation planning, agreements and strategies. We're doing quite a lot of work now on feasibility and comparing strategies to think about what an organization's return on investment could be for these very tangible and practical improvement actions. And lastly, I thought I'd just kind of note some of the hopes that I have for the future of this kind of modeling, and maybe some opportunities that you all would engage on or have other suggestions on. In general, I think I see the increased use of IBMs, not only in these complex systems, but in systems where we have very little information. Also, where I think we're going to see the increased use of IBMs in open platforms, particularly as we begin to reuse code and share code a little bit more. We're also seeing a bit more training in IBM literacy in academic communities and in practitioner communities. I think there's opportunity for a bit more integration with other models and algorithms, data and methods from other disciplines. And there's, I think, a lot of room for new tools that make tuning and calibration, verification, and evaluation of models a lot more streamlined and able to use the bigger data that are now available to us. Tech transfer tools, visualization, and novel user experiences are something I think could be a real asset to having non-modelers really understand these kinds of model systems and gain confidence in using them for real-world applications. And I'd like to give some thanks to collaborators for the projects that I talked about, and the other projects that I didn't get to talk about today that are in the photos, and to Computational Ecology Group team and the NREL CSU lab, and all the people that we're working with to kind of try to advance how we tackle problems in computational environments. Thank you.
Yeah, thank you very much. Lauren, you have a question?
Yeah, I'm really curious about, so the individual based models, if you have a lot of rich information about one particular species, you can incorporate that in. I'm curious about scaling, on, multi-species environments where you maybe don't have as much life cycle information, or if you're trying to work, with some of the platforms like GBIF data. It seems like an individual based model might be a lot more complicated to produce when you're starting to deal with many species at a time. So could you talk about, some of those challenges, and then maybe, some of the comparisons with alternative non-individual or agent-based models, and why you would go with, an individual-based model over those?
Yeah, I think you're right that as you add more individuals representing the community in a realistic and dynamic way is an interesting challenge. We've done small assemblages of species and models before, but as you're representing more and more individuals, I think you have to have the information to parameterize the who eats who, and if one species isn't available to eat another, what happens? What happens to predator and prey situations or communities or things like that? If they're not so much interacting but just living in the same environment, I think I think you can follow a very similar approach to single species models, just layering on multiple populations within the same environmental space. I think some of the advantages of using an IBM are to be able to look at the interactions among individuals and environments and have one environmental system model driving multiple changes for different species. There are other ways to do these things, like you can use state and transition models to focus probably a little bit more on the environmental change and less so on what that means for like population and demographic changes and the mechanisms of how that impact cascades to multiple levels. Does that fully answer your question?
Mostly. I think trying to understand if I have occurrence records, for a set of species, tracking, like the examples you gave of tracking movement, do you require that ability of understanding movement and life cycles in order to be able to leverage an IBM. And so, if you only have occurrence records, maybe that's when you go for other occupancy model, or if your presence only data, your Maxent or other habitat suitability models. So I'm just trying to understand, what information is required to make an individually based model go, and where is that, a limiting factor in terms of being able to use them.
Yeah, I would say that data is generally not the limiting factor for an IBM. You can create some incredibly simple models, like they can even be more like cellular automata kind of situations. They don't have to be rich, detailed things that require specific factors. I would say the question more drives the choice of framework than the data limitations. We could we've constructed fire models, and we've constructed disease models that don't even have animals in them, vegetation recovery models, and so forth. So I think it's more just, how do you want the model to work, and the question you ask of it rather than the data. Stats are great for developing relationships. So occupancy models are good at, that kind of question. They're not so good at some of the other kind of questions, like how does, disparate data interact to affect other processes.
So coming back on the data, but now some of the speakers we had earlier are talking about you putting various sensors in animals, and part of the motivation is targeting that one species. The other motivation is that you just have a capable moving sensor throughout the ecosystem, looking at everything in the ecosystem, because most species are correlated. I guess, to what extent is that usable when you have these proxy sensors on species that you can monitor, monitoring other species?
So you're talking about if we go and like GPS collar an animal, what can we?
Yeah, that's a good example. Or like the bulls you had at the very beginning. They measure tall trees inherently, because that's the only way they can live. I'm not sure to what extent they measure other species that are symbiotic with them.
Yeah, I'm not quite sure how to answer that, but I think in general, species can be proxies for other species, although there are some limitations to that. So, we know sage grouse, we know where they are, we count them every year in certain places. We GPS and track and collar them. They're supposed to be an umbrella species for a number of other organisms that also rely on sagebrush vegetation. But they're good at that at some spatial scales, like broadly. And once you get kind of zoomed into other spatial scales, some of those relationships fall apart. You realize that one species really needs something in particular that the other species doesn't well represent. And they use different locations on the landscape. So I mean, I think there's limits. There's some advantages, but some limits.
So then, kind of the scenario for that question was, you rarely care about these species in isolation. Like the big pictures, you have many thousands of species, and what I really am trying to understand is, how do you model all of them, or make individualized models for all of them, like somehow measuring the human impact of, let's say, oil development on the regional climate comprehensively? Because that's the big prize, but shockingly difficult.
Yeah, it is difficult. So I mean, there are approaches out there that focus more on biodiversity and intact landscapes and ecosystems and the services that they provide to communities. So that's one way to think about it and move forward. There's probably simulation models that you can design with that objective in mind. I haven't had as much experience trying to develop on with that kind of lens, but you're right. I think that the efficiencies gained by kind of looking at multiple species together in changing landscapes is an important way to go.
So then, how would you automate like the workflow you have right now? Because there's no way of doing like the kind of effort you're describing for thousands of species because we don't have the money.
So I think there needs to be some new tools that allow that automation, that can take pretty widely available data like GBEF and some just generic habitat maps or easy to create habitat maps that can be automated, and then kind of fuse the information together in landscape transition models to see what areas are kind of retained and what is not retained. I think you might in that scenario lose some of the detail, but that's a compromise that you can make to get to a much larger perspective.
Okay, so and what might those tools look like? I guess maybe one way of asking it is, how much is it expert opinion, which is expensive but really valuable, and how much of it is more data and search driven, which is scalable but dumb?
Yeah, it depends on the species, but I think the vast majority of what we put into these models is search driven rather than expert driven. I think there needs to be some amount of human designing the model, but a lot of the models for a lot of species are pretty similar. So I think there's some efficiencies to be gained by kind of looking at guilds of species or similar species within families that operate and move through the landscape in pretty predictable ways, and kind of ensembling together groups of like species and environments.
Okay, makes sense. And now one technology that may be relevant is like large language models, because I'm guessing, and tell me if that's correct, there should be a large number of verbal reports of how species behave that are presumably very difficult to collate into a simulation, but presumably exist in either published literature or just people talking, like bird watchers or something like this. To what extent is that true? Like, is that an opportunity for more data to be brought to this problem?
There's certainly a lot of information in the scientific literature that a language model could pull out. Verbal accounts, I'm not sure that people would build models purely based on verbal accounts unless there was no other information. So, but I would say like there's a lot that we could speed up just by not having to search quite so hard for all the information, not having to build all the models from scratch, not having to kind of go through all of the painstaking repetitive tasks that we do to build one of these models. And so, yeah, I think new tools and ways of speeding things up, tuning, using some AI or machine learning that allows us to kind of incorporate the wealth of information that we do have that we would spend a lot of time doing pre-processing on, and just kind of pull the pattern from an algorithm, for example, might help us translate that into what do we want the movement to look like, instead of combing through the literature or interviewing experts. So those are the kind of things that I'm excited about.
Okay, so, and are there additional data sources or let's say sensors that would make your life easier?
Yes, if we could wire up a good selection of organisms, from trees to mostly animals, and have them move through the landscape and just record all that data and use some pattern recognition algorithms to really understand what they're doing and why, that information really could drive a lot of what an IBM looks like. So right now, animal GPS tracking is pretty limited. It's expensive. The loggers are often a bit large and pricey, and I think I don't fully understand the reason for that. It seems like there should be a much lower cost and a lot more data available in this day and age for that problem.
Fair. And Lauren?
Yeah, on that point, I'm curious as to whether or not camera trap data, like if you have an array over an environment of camera traps, if that's been incorporated into some of the work that you're familiar with. Because we have a platform here at Google that we help support that's a multi-institution collaboration called Wildlife Insights that does AI over camera trap images, and there's data hosted there. And so I'd just be curious as to if that's a source of potentially scalable information over an ecosystem that could work in conjunction with an IBM.
Yeah, I think it could, particularly in figuring out where animals have passed, where they've been, where they occupy, where they spend most of their time. There's all sorts of questions that you can answer with camera trap data. How different are individuals and so forth. Yeah, that's an interesting thought.
That makes sense. Yeah, well, thank you. I mean, I don't know if you have any other final comments, but yeah, this was fascinating.
Well, thank you both for your insightful questions.